Right, yes. Okay, hello and welcome back to one of my brief primers on chemistry. This is looking at the atomic structure again. We're looking at, this time, atomic number and atomic mass and isotopes. So what I'm going to do here, whereas historically I have picked on helium, beforehand I picked on helium, but this time I'm going to pick on hydrogen. Hydrogen is going to be very pertinent. So if I just quickly draw hydrogen, hydrogen's the simplest to draw, a simple proton in there and a simple electron up there. There we go. You want the orbital? Oh dear, my 8-year-old does this far better than me. Really. Touched this for the first time this morning and he can do this a lot better. I wish I could, maybe I can move that around. Hold on, I can do that. Let's not digress too much. It's never going to be perfect, but let's try and get it tidy. Get rid of that. And then see if we can put that more in the center. Well, that's as good as it's going to get, I'm afraid. I'm a scientist, not Da Vinci. Right. So there we are. This is hydrogen, the simplest form of hydrogen. So if I write that here, this is hydrogen. Okay. And what is the chemical symbol of hydrogen? Anybody? Yes, it's H. Right. Now, when you look at the atomic symbols in a periodic table, you'll generally see there's two numbers by them. You've got a number up here. I'm going to call that A. And you've got a number down there. I'm going to call that Z, method to my madness. So essentially what you've got here is you've got the atomic mass, which is denoted by A. So the atomic mass which is A. And you got the atomic number, sorry. Thought I'd made a bit of a what's it there, but I hadn't. Equals Z. So the atomic number simply denotes the number of protons there are in the nucleus, okay? So in this case, there is one proton in the nucleus of hydrogen. And the atomic mass denotes how many protons and neutrons there are in a nucleus. Now remember this, that the whole mass of an atom is the number of protons and the number of neutrons. Electrons are so light, they don't even figure, really. The mass of an electron is nothing compared to the mass of a proton and a neutron. So we don't count them here. Make no mistake, electrons are still important. I mean, the whole theory of chemistry is based on them in one way, shape or form. But for this, electrons are not heavy enough. They're lightweights, they're featherweights, they're not even that. We are only interested in protons and neutrons. So if we can just summarize that here, this is recording, so don't be trying to make any notes here. So we can say that atomic mass, this is why I prefer PowerPoint, is equal to protons plus the number of neutrons. There we go. And that's why that therefore tends to sit over there as the A. This is the larger number. And obviously the atomic number is the number of protons. I better write that down, hadn't I? Atomic, you're having a good laugh here, aren't you? Atomic number is number of protons. There we go. Right, so what's this got to do with isotopes then? Right, well, I think I said before that if you change the number of electrons, you change the charge of the atom. So if you chuck in more electrons than you've got protons, you end up with a negatively charged atom, which you see a lot more with the nonmetals. And if you take out the electrons, then you end up with more protons than electrons, which means you end up with positively charged atoms. Yeah. Obviously, positively charged atoms for giving hydrogen is mainly metals, like sodium plus, potassium plus, Ca2 plus. I'll stop there. And obviously, you know, you've got the likes of fluoride or F minus, Cl minus, as in chloride, fluoride, iodide. You get the general idea. Those guys have got the electrons they've taken, and the metals have got the electrons they've lost. More about why they want to do that later on, but let's just accept that here for now. I must remember I'm speaking to A-level, not to GCSE. I don't mean to patronise you. Right, so if we change the number of neutrons, what we're doing is we are effectively changing the type of element. So the element stays the same. So if we therefore take our mate here, our hydrogen, let's see if I can do it again, as its lowly electron, and I'm going to stick its proton in here and a neutron in here. Okay, that's the one. And to save time, I'm going to do the same thing here. And I'm going to put another neutron in here. Sorry, proton, early in the morning for me. And then I'm going to put another neutron there and there. Okay, so what we've got over here is still hydrogen. Okay, and it's still hydrogen. Why? Yeah, that's it. You've got it, because it's still got a single proton in there. If you put another proton in there, it would become helium. Exactly. I mean, the fact that it becomes helium plus is neither here nor there, but you know, it would be helium. But anyway, you've only got one proton in here. We're keeping to the one proton, but we have added a neutron. So this now becomes an isotope of hydrogen that we give the chemical element of D2. And we can assign it as, what would the atomic mass of that be then, ladies and gentlemen, boys and girls? A proton and a neutron, 1 and 1 is 2. How many protons? 1. So we'll put a 1 in there. And that is deuterium. Can't spell deuterium. Oh, I tell you what, because I'm on a live audience, let's not be too sloppy. Let me just rub that out. This is what I love about this. If it's paper, I'd be a mile high in waste. Save the environment. So DEU deuterium. You get the idea. You can Google it if you're not really so sure. Yeah, deuterium. Yeah. Otherwise, I'll be here all day. And here we have got another one with another neutron in it. So that gives us an atomic mass of what? 1, 2, 3. So 1 proton plus 2 neutrons, da-di-da-di-da, gives us tritium. And it's going to be 3 over 1 tritium. Now, so these therefore are the 3 isotopes. I've already kind of written that up there, but let's just, for completeness, I'll do this for you here. So these are the 3 isotopes of hydrogen. You only see hydrogen, this, in the periodic table. But as with other elements in the periodic table, they do have related cousins. So in this case with hydrogen, we've got deuterium and we've got tritium. Now, believe it or not, I mean, even though hydrogen is the most common isotope of the hydrogen family, deuterium and tritium, you have consumed it. I mean, it is still in your water. It is still mixed up with hydrogen as a whole. I mean, you may have heard of something called heavy water. That's this, D2O. You can equally get D2O. And obviously what we're familiar with, H2O. And these are all chemically similar versions of water. Obviously, the Puritans will say you can probably get HDO as well. You can do, but obviously there'll be varying abundances of each of the versions of water in the liquid. This tutorial isn't about that though. But you can get different forms, and even though at the end of the day they contain different numbers of neutrons, they are chemically the same. So D2O should behave the same as H2O, should behave the same as D2 as T2O. So chemically, they'll behave the same. In fact, the only real difference is, if you want to know them, please don't forgive me if I don't want to scribble this lot up. So isotopes have, which are the same, is therefore going to be the number of protons, obviously, the number of electrons, And the chemical properties are going to be the same. Don't forget this is being recorded if you're trying to scribble this down. And what is different, well, it's going to be obviously the atomic mass is going to be different because we're changing it, aren't we? The atomic mass A is going to be different. And obviously, if you really could be a Puritan, number of protons, we could have said atomic number. I can hear some people hollering that out. And obviously, number of neutrons is going to be different. And the physical properties will be different. They're heavier. Okay. So that basically is pretty much what isotopes are. And the physical properties may be different. For example, these will be of different weight, obviously, but chemically they will be the same. We are still dealing with hydrogen all the way through. Hydrogen is as much, deuterium belongs as much to the hydrogen family as tritium belongs to the hydrogen family because they are the same element. Okay, if you stuck another proton in there, you'll end up with helium. We're not sticking another proton in, we're sticking in neutrons. So that is basically how we're doing it. And I should also have said here, because I know somebody spotted a deliberate mistake, we also have the electron in there. There we are. I was waiting for somebody to point that out. So I hope that has demystified it a bit for you. I think areas where I always found a bit confusing was the way around it goes. So notice the bigger number, the mass goes at the top, and the lower number, the number of protons goes at the bottom. And yeah, I mean, that is also quite important to understand and learn too, because that's pretty much how it's denoted in the periodic table. So that's how it's written. So hopefully that gives you some understanding there. Now, here's a little piece of homework for you, slightly unrelated, but when you next look at a periodic table, look at the atomic number now and see how the atomic number increases or changes going across the periodic table. You'll be interested to know about that. Okay, and we'll discuss that at a slightly later tutorial. In the meantime, I hope this has been informative for you. If you can't understand my handwriting, I'll upload something in voice in the post. But at least either way, you've got my voice. This has been recorded, and you've got me if you want to ask me any questions. Mums and dads, I've borrowed this from Pearson's A-level chemistry, but something is fundamental be relevant across the exam boards. Okay, guys, thank you for watching, and take care for now. Thank you.